Hello, I see that Professor Poisson has joined. Good morning, Professor Poisson.
Good morning, I'm here.
Yeah, I was just checking with everyone how it's going. Uh, so, what I will just do is, in case anyone has any questions, I will just allow them to ask right away.
Yep, sounds good.
So, Oindrila, you wanted to get it clarified from Professor Poisson. You had some question about the notation of Legendre polynomials. Let me just yeah. So you can go ahead and ask if uh, what I had said
Hello.
did clarify the
Yeah,
thing. Yeah,
can you hear
please
me?
go ahead. Yes, yes.
Yeah, hi, Professor Poizo. I had a basic confusion in the preliminary equation 1.2. So when we are going from there to 1.3 and 1.4, I am not understanding the two angles theta and theta prime, how they are related to the angle gamma between r and r prime.
Right, so there's, yeah, I didn't write down the formula for this, so you're right. So the vectors r and r prime have their own angles relative to the coordinate system. So we have two sets of polar angles.
Yeah.
But I'm not sure if you need to work, let's see. So gamma is the angle between the two vectors. So r and r prime, make an angle between the two directions, and gamma is that angle. So it's not too difficult to work out the relationship between these things by just working out, the scalar product between r and r prime. So you can figure out, so cos gamma is basically the scalar product between the two vectors divided by the length of each vector. So you can work out the formula if you need it. I'm not sure if you need it, but that's how you would do it.
Okay, thanks. I'll do that. Thank you.
Yeah. So there was another question by Alice. Alice, you would want to go ahead and ask?
Yeah, hello, can you hear me?
Yes.
Yep.
Please go.
Yep.
Yeah, no, my question was just to, maybe we can go through the test three, because let me see the text. So I tried to solve it using the potential described in the Newtonian potential, but I wasn't sure it was the right method.
Okay, so before we
I-
go to task 3, did you complete the previous tasks?
Is it a question just for me, for everyone?
Well, so in principle, you're supposed to go in sequence, right? You first tackle
Yeah,
1 and 2, and then task 3 will be relying on the results you find for the previous ones.
Yeah, I tried to complete the other ones. So what I did for the task 3 is to use the equation 2.6 and the Newtonian potential 1.
Okay, let me see if I can look at those equations. So you're saying, let's go back to task 1. So you've completed the, so task 1 was about deriving the equations that I showed there. So you have found the solutions in 2.5 and 2.6?
2.6. Yes, I haven't tried the wall calculation, actually. I think I understood the method.
Okay, so task 3 is relying on those results, right? So you have to use the previous results in order to complete the task. And I don't think you're meant to rely on the Newtonian potential except as a rough guide of what a rough indication of what those solutions mean in the relativistic context. So you're supposed to maybe compare the relativistic solutions to the Newtonian ones when R is large compared with M. So that, that gives you some guidance about the meaning of those solutions. Okay, but keep asking. So I haven't listened to the full question yet.
Yeah. So which solution exactly are we comparing? The 2.6, I guess.
Well, so the general solution is going to be a combination of 2.5 and 2.6, right? So you have two particular solutions, and in principle, you have to add, you have to consider a superposition of those. And the idea would be to try to figure out which combination of those solutions gives you something that resembles, the solution 1.9 for the Newtonian potential.
1.9. Ah, okay. What 1.9? 1.9 is related to love number.
Right.
The task 3. So shouldn't I use the 1.9 for task 4? And no, sorry, for task E.
Oh yes, you're right. You're right. Yeah, for task 5. No, you're right. Sorry, I was skipping ahead.
Task 5.
Okay, yeah. So that's right. Okay, sorry about that. So yes, so for task 3, we're supposed to be comparing to the potential of 1.3. You're right. Sorry. Yeah.
1.3. Ah, okay. So it's the Newtonian potential.
Right. That's right.
Ah, okay. Okay, I wasn't sure. Okay, thank you.
Okay, so sorry, I'm not sure if I really answered your question because I don't think I've really listened carefully to your question. So are you okay?
So I'm not sure if I understood how to proceed very well. So I think so through equation 1.33 I can find the quadruple momentum. So and then I can use equation 2.1. Is it correct?
And 2.1. Right. Yeah.
Okay. So I think I understood how to proceed then. I think
right.
so.
So the idea is that if you want to calculate something that would have the interpretation of describing a quadruple deformation of a black hole, you're looking for a perturbation that at large distances would behave as 1 over r cubed. Okay. Because that's what the Newtonian potential does. So you're looking for a relativistic version of this. So at large distances, when r is very large compared with m, it should have that 1 over r cubed behavior. And you're right, the coefficient in front then will tell you what the quadrupole moment of the black hole would be. So so the idea is to look for those solutions that are given in task 2 and ask which is the one that would have this behavior at large distances.
Okay.
So was that helpful or not helpful?
So when it asks, is this solution acceptable physically, we should look what happened for large distances, or for
so at large distances you can identify the type of solution you want, but then the solution has to apply everywhere. So for to understand the physical acceptability of the solution, you have to look everywhere and see if there are problems with that solution somewhere. So that's the idea, to try to analyze the behavior of the solution, not just at large distances, but everywhere in the space-time.
Okay. So like for R equal to m.
For example, yeah, that would be a very good place to look to see if there might be problems with that solution.
Okay. Okay, thank you. I guess
Okay, yeah.
I have a better idea.
Okay, very good.
Okay, thanks, Alice. Anyone else has any clarifications or questions about how you have proceeded so far for Professor Poisson?
Yeah, so it seems that it's clear to everyone.
Yes, yeah. Okay, so if no one, I was also checking if anyone tried using, say, Mathematica or something, some package for attempting any of these expansions.
Yeah, that would certainly be helpful because, for example, the solution of 2.6, if you want to verify the large distance behavior, you have to deal with the logarithmic term, you have to expand that, and then you have to expand the polynomial. And there's a lot of cancellations that occur when you do this. So you have to, as I indicate in the notes, you have to do an expansion to 5 orders in order to get rid of all the cancellations and get the dominant behavior, which I indicate is 1 over r cubed. So yeah, to have symbolic manipulations, to do that on a computer would be very helpful. And the same goes for solving those differential equations in the previous task. If you can do it by hand, then I'm showing you ways to do it by hand, but that's, it's a lot quicker, of course, to do it by computer.
Right. So I would just check with my colleagues, Sriram and Chandra, do you want to ask anything regarding the problem set or the lectures? I've already written something for the participants.
I don't have anything, Dawood. I'm partly through the problem. Unfortunately, I haven't made as much progress as I would have desired.
Yeah, it takes some time. It takes some time, and it's not something you need to do necessarily in one sitting. But for the students who really want to absorb the material that I gave in the lectures and really want to get a handle or get a good feel for what it means to do perturbation theory, I think it's a useful exercise to go through, and I really encourage people to do it.
I could read through the problems, but I haven't dirtied my hand as much as I would have liked to. I would like to spend more time with it. Yeah. I'm sorry about that.
No, no need to apologize.
So I had a quick question, Professor Poisson, about the last comment that because the issues appear mostly at r equal to 2m and the Schwarzschild coordinates themselves are sort of not well behaved there.
Right.
It's better to do it in the advanced coordinates.
That's right.
Yeah, I was just curious how messy the equations are in advanced coordinates. Do they also simplify the equations you give in the appendix, for example, the perturbation equations?
So it would take some effort to transform those equations from the the TR coordinate system to the VR coordinate system, but I don't think they would look any more complicated. They would just look like more or less what you see there, except that there would be slightly different factors and slightly different derivatives. But more or less, they would look like the same, almost the same equations. But the point is that you don't really need to transform the field equations. You can still continue to work in those coordinates. But once you have the solution, then it's much easier to transform the solution to the new coordinates, and that's what I'm suggesting in that last task, so that you just take the solutions and re-express the solution in the new coordinates. And that's basically just a matter of taking the components that were previously computed and just combining them in the right way, so that you have now the new metric components in a new coordinate system. So it's just combinations, algebraic combinations of the previous components. So that's a pretty simple task that doesn't require, reworking everything.
Okay, thanks. Thanks, Professor Poisson. Chandra, you had any questions?
Sorry, I'm connected through a couple of devices here. Sorry, not related to the problem set here, but if I may, I had a naive and a pessimistic question regarding the perturbation theory.
Okay.
Yeah. Yeah, so in some sense, the question is like, what's completely hopeless for, let's say, PN approach when we think of it, or perturbation theory approach, like, where we should stop, kind of thing.
Right. So you're certainly right to suggest that perturbation theories have, limitations. And the limitation is, well, for one thing, it's practical, right? So in post-Newtonian theory or in black hole perturbation theory, it's possible to calculate, at first order, second order, third order, fourth order, but it becomes increasingly hard. And when I see the mass of effort that was put into the post-Newtonian calculations throughout my career for the last 30 years, I'm really, really impressed at how much people were able to do. But it was extremely difficult first to reach 2.5 post-Newtonian order, and then to push it to 3, and then 3.5, and then, the current state of the art, which is 4. I mean, people are pushing this, and it takes a massive effort that spans, years. So practically speaking, it gets progressively harder. And if the task were to go to 10 post-Newtonian orders, I would say that this is hopeless. There's no way that anyone in a reasonable lifetime would be able to achieve this. So that's a limitation. There's also a more fundamental limitation in that, for example, if you wanted to use post-Newtonian theory to calculate what happens to a massive particle that orbits around a black hole and is about to go through a transition from orbital motion to plunging motion, we know that the relativistic orbit around a black hole gets mechanically unstable when the orbit is too close. So as the in-spiral proceeds, you transition from circular motion, the inspiraling type motion, to a rapid plunging motion. Well, that occurs around 6m or thereabouts, between 4m and 6m in the Schwarzschild solution, in a Schwarzschild spacetime, and that is a place where post-Newtonian theory really has no hope of giving you any meaningful answers, because velocities are very large, significant fractions of the speed of light. the gravitational field is very strong. So in that regime, while post-Newtonian theory will probably fail at giving you any reasonable estimate of what happens during that transition, or and beyond the transition. So there are limitations like this. For perturbation theory, for black hole perturbation theory, well, it's it's reasonably easy to calculate at first order. For example, if I'm using the mass ratio as an expansion parameter, it's a lot harder to calculate at second order, but people have made a lot of progress, again, in an effort that spanned at least a decade, to learn how to calculate the second order perturbation using the first order perturbation as a source for this. And that is, both useful and necessary to do calculations involving extreme mass ratio in spirals, where you want to go beyond this approach that I described, where the motion is perfectly geodesic in the background space-time and you calculate the perturbation. Now you want to have the perturbation act back on the particle so that it actually inspirals instead of staying on a fixed orbit. So that's the whole self-force program that was alluded to during my lectures and during the introduction. So in order to incorporate all of this, you have to go to second order, and it's a very difficult problem. And again, there's been tremendous progress over the last 10 years, but it took a massive effort. If the task were to go to third order, I would say that, well, I'm not sure if it's conceivable that anyone in a reasonable lifetime would be able to achieve this. So, so that was a very long answer to your question. So each perturbation theory approach, each method of approximation has limitations. But as I said, you can use all of those limited approaches and make them work together and feed information back and forth between different approximation methods. And in this way, you can actually find yourself being very surprised that the methods which you thought were limited are actually less limited than you thought. So you can really buy yourself a lot of additional knowledge and additional results by allowing different methods to be compared and to be communicating among each other. So because of that, my view is not pessimistic. I think that there's a way of doing a lot without having to say let's just rely on numerical calculations. Doing a numerical calculation of the a numerical solution to the field equations. I see that Eric is in the audience. He can comment on this, but the numerical methods have limitations of their own, because if the orbital separations become too large, it takes a long time for the system to do anything. And there's a good chance that your supercomputer will run out of memory by the time that, even a very small part of the orbit will have been, described. Numerical methods have a problem with small mass ratios, because if you have a large black hole and a very small black hole, you still need to resolve the scale of the small black hole, knowing that it's moving in the field of the large black hole. So that creates a computational challenge that is difficult to meet. I mean, people think about ways of circumventing this, and people are very clever about coming up with all sorts of strategies to do this. But the point is that there's not one method that can be used in all regimes, practically speaking. So you really have to rely on multiple approaches to the given problem.
I see. So if I understand, so the consistencies has to be compared with numerical results eventually. Is that what you're suggesting?
Yes, well, that's one way of doing it. But I'm saying that the post-Newtonian approach can be compared to the self-force approach. And in the common regime where they both apply, you can compare information back and forth. And in fact, you can complete the information. There are things you might not have been able to compute on this side that you were able to compute on this side. And by joining them in a common region of validity, you can pass information back and forth. So this cross comparison has been extremely fruitful in the past to check methods, but also to improve methods by passing information. And that can be done with numerical relativity as well. And there's been a lot of effort trying to make sure that all of those checks have been performed to calibrate everything, right? Calibrate everything against each other in the best possible way, where you learn the most from doing these comparisons.
Right. Right. So forgive my ignorance about the self-force approach. So when we talk about this second order perturbation, do we talk about the perturbations of G, or do we talk about perturbations of the mass ratio parameter?
Yeah, so for self-force, it's really an expansion in powers of the mass ratio. Okay. So we have the Schwarzschild, the curved space-time that dominates. Then we have the perturbation created by the small body. So we have an expansion parameter given by the mass ratio. And then we go first order, second order in that mass ratio.
Okay, okay. Thank you. Thank you very much.
Yeah, no, you're welcome. That's good.
So thank you very much, Professor Poisson. I think we are almost towards the end of the session. So we'd just like to thank you for your wonderful set of lectures. And we will move on to the closing ceremony. I think Chandra will take over from here. Before that, I'd like to thank you and all the other lecturers